Mr. B. Dhanasekar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are having the subject compiler design. So, we are studying the parsers nowadays, the LR parsers. So, which is going to be one of the efficient class of parser coming under the bottom up parser category, within which we had seen three types of parsing table constructions. One is the simple LR parsing table construction, the second one is the canonical LR parsing table construction, and the third one is the look ahead LR parsing table construction. So, first of all we should study that is how the SLR parsing table is being constructed, and once the parsing table has been constructed, we know that is how to parse the strings with the help of the parsing table. So, for the construction of the SLR parsing table, we know that there is a need for collecting or identifying the set of all items available in the various states of the equivalent deterministic finite automata. So, for the construction of the LR of 0 items, we need to have a few functions. So, actually you will be given the grammar which will be once again converted into the augmented grammar, and the reason for the conversion of the given grammar into its equivalent augment is just for incorporating the accept action inside the parsing table, which is missing as far as the predictive parsing table is concerned. So, that is the reason why we convert the given grammar into its equivalent augment grammar by introducing an additional production S dash tends to S, where S is the start symbol of the grammar. Whenever we are trying to reduce the S into S dash, it will invoke the accept action saying that the parsing has been completed. Today we shall see that is how the LR of 0 items are constructed, and first of all we shall see that what are the functions being used for constructing the LR of 0 items. So, the first one, we have the function called procedure items. What is given for that function is the G dash, which is nothing but the augmented grammar of the given grammar. So, the C stands for the canonical set of items, or it is items, which will be constructed from or initialized from the function called closure of S dash derives dot S. So, S dash derives dot S is an item. Actually the production is S dash derives S. When you place a dot there, already we have seen that this dot is telling how much of the prefix has been already recognized. So, what is so far recognized and what is yet to be recognized. Since we are finding S dash derives dot S, the whole process is yet to be started. That is the meaning of having a dot on the extreme leftmost end of this right hand side. So, what this closure says is, so we need to find out an item of the form A derives alpha dot B beta, and which is supposed to be in a state called I. So, the what it means is alpha is any prefix having any, that is combination of variables and terminals or anything, dot followed by a variable, that is very important. So, you will be having closure expanded to further more items only if dot is followed by a variable. So, here we find an item of the form A derives alpha dot B, where B is a variable followed by anything else. If it is in I, then we should know that for this B, since it is going to be a variable, so there will be a right hand side for that. The right hand side for this B is the gamma. So, if B is a variable, there exists a production of the form B derives gamma, which is supposed to be in the given grammar called G, and now what should be added into the closure of this state I is b derives dot gamma, provided it is not already there in I. So, that is the meaning of this closure function. So, you find an item of the form a derives alpha dot b beta in the state called I, and this B may have even more number of productions also. That is the reason why each production B derives gamma, such that if B derives dot gamma is not already there in I, then we are adding B derives dot gamma into the state called I, and repeat this job as long as more items could be added into the state I. Whenever you find it is not possible to add more number of items into the state called I, then we will return that as the output. So, that is the use of the closure. So, closure will try to expand the current state by introducing what are all the possible directions in which we can have, that is what are the possible that is expansions from the current state. So, since dot followed by a variable is obtained, this variable could be expanded with all its right hand sides if it is having more than one, and every possible that is expansion will be introduced into the current closure. And now, if you are having the start state, we are starting with the closure of s dash derives dot s, and for that we will be having some set of items, and all these items will be available in the first state of the that is equivalent parsing table. The first state has the set of all items which are obtained from the closure of s dash derives dot s. So, now the question is, how will you find out the rest of the states? The parsing table itself is having some number of states, that is defined in the size of the parsing table. The first state is obtained by using the closure of s dash derives dot s, and the rest of the states are obtained by using once again the algorithm for items. So, to find out the rest of the states, we are going for each set of items I in C, where I stands for the state and C stands for the canonical collection of all the items, and for each grammar symbol x, now we are having two parameters, which state we are in, that is I, and a grammar symbol x. So, if you are in the state I and for the grammar symbol x, so what will be the next state? That is what we have to find out. So, for each state I and for each grammar symbol x, so now we are computing another set called go to of I comma x. So, this will give you another set of items. So, if it is non-empty, another one is if it is not already in C. There are two cases. The first thing is it must be non-empty. The second one is if it is not already in C, then we will introduce another state into that. That is what we are doing, add go to of I comma x onto that is C. So, we have got the first state from the first line of the code, our algorithm, closure of s dash derives dot s, and the rest of the states are computed by getting into this loop, where from I for x, what is going to be the output? If the output is the one which you already obtained, do not introduce a new state, and if the output is empty, once again do not introduce a new state. So, if neither of them is true, then we will go for adding go to I comma x into that is C, and repeat this job till you generate all possible states available in the equivalent parsing table. So, that is what this algorithm is doing. And as far as go to algorithm is concerned, I said already it is having two number of parameters. One is going to be I, that is the current state, and the second one is x, which is going to be the grammar symbol for which we are computing the transition. Now, so I said it is going to be either empty or it is the state already we have generated. So, when we will be having an empty output, that is empty set as an outcome of go to of I comma x. So, we are looking for an item of the form a derives alpha dot x beta. So, if it is going to be a derives alpha dot x beta, followed by dot, we have a symbol. If it is having a symbol, definitely the closure is not going to be empty. Suppose if you are having dot on the extreme rightmost end of the item, for example, if the item is of the form A derives alpha x beta dot, then the closure will be empty. So, if A derives alpha dot x beta, then there exists a non-empty set of items as an outcome of the goto of I comma x. So, we have located an item of the form A derives alpha dot x beta, where x is immediately following dot, which is nothing but the second parameter of goto function. Now, we have to find out what is going to be the closure of this. Closure of not the same item, we move the dot one position towards the right. As a result of that, we will be having another item called A derives alpha x dot beta. Actually, we are applying the goto function for alpha dot x beta, but we return the closure of alpha x dot beta. That means, we have made a transition from the previous position of x to the next position of x. So, this is what the function being used for the goto of I comma x. So, we have seen actually three number of functions. The first one is the function items, which is actually responsible for computing the entire collection of canonical LR of 0 items, which are actually produced as the outcome of the given grammar, which in turn uses another function called closure. So, which will be computing all possible, that is, items which can exist on the current state. And the third function which we have used is going to be the goto function, which will be computing the actual transitions. So, from the current state, what are all the resulting states which can be reached for various grammar symbols. As far as finite automata are concerned, we compute the transitions only for that is terminals, but here in this kind of deterministic finite automata, which is an equivalent for the SLR parsing table, we compute the transitions even for variables also. So, both for variables and terminals we compute the transitions, which means that from the current state we have to find out the set of all possible, that is, next states by moving dot from the current position to the next position, provided such a position exists in terms of either a terminal or a variable. So, now we are keep on generating the set of all states until we find a state where we cannot go for generating any new state, which means that all the states available in the corresponding or equivalent that is grammar are completely generated. So, once all the states have been generated, by using the canonical set of items, that is C, we can go for constructing the SLR parsing table. So, we used an algorithm for computing the LR of 0 items, and once the LR of 0 items are obtained, that means your canonical LR of 0 items or simply the items are obtained, then you just invoke the algorithm which will be used for constructing the SLR parsing table, which in turn will give you the SLR parsing table, and once the parsing table has been constructed, then we can go for computing the, or we can go for parsing any string from the language of the grammar. The parser will succeed in constructing the parsing table provided the string is there in the language of the grammar. So, if it is not that, then it will that is report appropriate errors that is based on the intersection which be or which have been met in the parsing table based on the error. We should see that is what is going to be an LR grammar. Already we have seen that is what is an LL of 1 grammar. So, where we have that is shown that a grammar is said to be LL of 1, then the corresponding predictive parsing table should not have any multiple entries anywhere there. So, if the corresponding predictive parsing table does not have any duplication of entries, then we will be calling the that is grammar as LL of 1. A similar story is applicable as far as LR grammars are concerned, but we will define these LR grammars only based on the bottom up parsers, that is SLR parser or LR parser. We shall go for a short break, then after that we will continue the lecture. Welcome back. We are seeing the LR grammar. So, now to define the LR grammar, we are constructing the LR parsing table either by using the that is SLR method or that is canonical LR method or LALR method. So, if the parsing table has no duplication of entries, then we can claim the grammar as LR grammar. So, if the parsing table is obtained by using SLR method, then the grammar is called SLR. If the parsing table is obtained by using canonical LR method, then the grammar is called canonical LR, and if the parsing table is obtained by using the third method, that is LALR, then we will be calling the grammar as LALR of 0 grammar. So, now this is what the definition of your LR grammar. Construct the parsing table either by using SLR or by CLR or by LALR. So, if the parsing table produces as a result of this that is algorithms have no duplication of entries, then the grammars will be called as LR of LR grammars. So, we shall have the construction of LR of 0 items. So, the grammar given for you is going to be the unambiguous grammar, which is an equivalent for the expression grammar. E tends to E plus E or T, and T derives T star F or F, and F derives open bracket E closing bracket or ID. First of all, we should find out what is going to be the augmented grammar equivalent of that. I said that we will be introducing a new rule, which is going to be E dash derives E. So, rest of the productions are the same thing. We have just numbered these productions just because of we want to introduce these productions onto this parsing table. Because of the space constraint, we use only the numbers rather than writing the entire productions. First of all, we shall see what is going to be the initial state of the parsing table. The initial state of the parsing table I naught is obtained by closure of the new production added as a production into the augmented grammar, which is E dash derives dot E. So, we will be applying the closure of E dash derives dot E, and now we have to find out what is going to be the expansion for E. So, this E has two expansions, one is E derives E plus T and another one is E derives T. So, by the algorithm, if S derives dot S, S dash derives dot S is a production, for that S, if you are having expansion, then write all these productions for that S with dot on the extreme leftmost end. That is, if an item of the form A derives alpha dot B beta is there, then introduce B derives dot gamma for all gamma into the current state. So, that is the reason why we are having E derives dot E plus T and E derives dot T are obtained or introduced into the current state. So, it is going to be a recursive process. So, the closure of E dash derives dot E has these three items, and it is not going to be the end. We must go for once again expanding E derives dot E plus T. Here also, just next to the dot we find a variable which could be further expanded, but when we expand this E, we will get once again these two productions rather than any new addition. So, the closure of E derives dot E plus T is non-empty, but it is all there already in the same state. So, no need of introducing as new items, since every state is considered as a set of items. So, no duplication of items. But when you go for E derives dot T, we have T derives dot T star F and T derives dot F. Once again, for T derives dot T star F, we find the output as non-empty, but already there. So, we can go for T derives dot F. So, F is having two productions, F derives dot open bracket E closing bracket and F derives dot ID. So, all these items are there as far as the state number 0 is concerned. One important thing here we have to observe is, in all these possible items, we find dot is on the extreme left end, because it shows that no progress or nothing has been recognized so far yet to start all these processes. So, that is what we find dot on the extreme left end of all these items. So now we will find out what will happen with the transition for E, with the transition for T, with the transition for F, with the transition for opening bracket, and with the transition for ID. So all these things are to be computed as far as from the state I naught, but all these will be obtained with the help of function called goto function. So if you go for goto, so this is what your current state, that is your I naught. The first one is we compute I naught with the transition, that is transition for capital E. So two items qualify because of E dash derives that is dot E, we move the dot to the right of E to get E dash derives dot E dot, and no more items are possible because dot on the rightmost end. And the second one is E derives E dot plus T. So we will be having E derives E dot plus T. So now we can find out the closure of the first item, which is empty, closure of the second item, which is also empty, because next to dot we have a plus, we have a terminal, we do not have a non-terminal. That is the state number 1. And the next one is the state number 2, which is from I naught for the symbol that is capital T. So to find out the transitions, you find out the items in which T is just following dot. So T is following dot in two items, one is E derives dot T and another one is T derives dot T star F. In both the items, you just move dot next. So you will be having E derives T dot and T derives T dot star F. And the next one is we find out the computing the transition of F. When you go for the transition for F, there is only one item from where transition for F could be computed, which is T derives F dot, and the closure of this is also empty because dot is already there on the extreme end of the right hand side. That is about I3. So next we go for computing the transition for opening bracket. When you go for computing the transition for opening bracket, we will be having the item F derives, you will move the dot one position right, so you will be having opening bracket followed by dot E closing bracket. So that is what the first item available in state number 4. We have F derives opening bracket dot E and closing bracket. But when you compute the closure of this item, it is going to be non-empty, as we find that next to dot we have a variable following. So this variable is to be further expanded. Since we are having two productions for E, the two items are written here, E derives E plus T and E derives T with a dot on the extreme left hand. And now written the closure of E derives dot E plus T, which is already existing there, so no more addition. The closure of E derives dot T, which says that two more items are going to be introduced. One is going to be T derives dot T star F, another one is T derives dot F, and the next one is the closure of T derives dot T star F. So it gives two items, both are already existing, so no duplication. And when you go for T derives dot F, so its items are expanded now, that is F is going to be expanded. F has two items, F derives dot opening bracket E closing bracket, and another one is going to be F derives dot ID. So as far as goto of I0 comma opening bracket is concerned, we get a new state which is called the I4 with almost there are 7 items. So first item is obtained from the state number, that is I naught, for the item that is F derives dot opening bracket E closing bracket, and all the remaining items are computed or generated as a result of the closure of F derives opening bracket dot E closing bracket. So from the state number I0, we have computed now the transitions for E, then T, and then F, and finally for opening bracket. The only item which remains for the computation of transition is F derives ID, so which is going to be the state number I5. So we find goto of I0 comma ID, which is nothing but I5. The item is going to be F derives ID dot, since dot is on the rightmost end of the right hand side, so which has no more items as a closure, so that is going to be the end of state number I5. So we started with the state number I0, and then we have computed the transitions for all possible items from this state, that is state number I0. So, we have got around there is 5 more additional states I1, I2, I3, I4 and I5, and from many of these states we can even find out the resulting states as a result of the transitions. So, in some of the states like for example, if you are going for I5, we find an item of the form f derives id dot, we cannot find out any more transition, but other than that particular state all the remaining states are having further transitions. So, now we shall see that is how we are computing the transitions from the remaining states. For example, if you are thinking about the I1 state, we compute the transition for plus, which is going for another state called I6, where the items are E derives E plus dot t, because plus is the symbol for which we are computing the transitions. We move the dot one position towards the right, then t is to be further expanded. So, we will be having t derives dot t star f, then this t is to be expanded, we will be having t derives dot t star f duplication, t derives dot f, and for this f we have to expand, which gives you f derives dot opening bracket e closing bracket and f derives id. So, this if you expand we will get empty because it is a terminal, and this if you are expanding we will get once again a empty set since it is going to be a terminal. So, that is about your I1. Then I2 we can compute the transition for star. So, that is going to be I7, which will give you an item of the form t derives t star dot f, expand this f to get f derives dot opening bracket e closing bracket, its closure is empty because dot is followed by a terminal, and f derives dot id, its closure is also empty because followed by dot we have a terminal. So, I4 for capital E we get that is I8, we will be having f derives E dot opening bracket E dot closing bracket, that closure is empty because dot followed by a terminal, and E derives E dot plus t, and the closure is also empty because followed by dot we have a terminal. And if you look at I4 comma t, we find the set of all items are already in I2, so it is not needed to go for a new state. Similarly, for I4 comma f we get a state which is going to be I3, so that is also going to be an state which we have already generated. And similarly, for go to I4 comma opening bracket we get I4, the same state is being obtained as a result of that, and I4 comma id, that is f derives id dot will be the output, that is going to be your I5. I6 comma t, which is going to be a new state, so numbered as I9, where the item is going to be e derives e plus t dot and t derives t dot star f, and from here also we have another transition for star, that is I9 comma star will be computed. So, that is the last one here, I9 comma star is computed, and then I6 comma f is going back to I3, I6 comma closing bracket, I6 comma opening bracket it goes back to I4, then I6 comma id goes to I5, I7 comma f goes to a new state called I10, where the item is going to be t derives t star that is f dot, and go to of I7 comma opening bracket is going back to I4, go to I7 comma id goes to I5, then go to of I8 comma closing bracket. So, it is going to be a new state once again, it is called I11. So, I11 means it is going to be the item is from your I8 is having f derives opening bracket e dot closing bracket, so which will be transformed into f derives opening bracket e closing bracket followed by a dot, and finally we are having I8 comma plus. So, I8 is here, that is plus, so we will go for another state called I6, then I9 comma star, so we have another state called I7. Then when you are looking at I10, so we have an item of the form t derives t star f dot whose closure is going to be empty, so no new additional states, and when you go for I11 we have a state we have an item of the form f derives opening bracket e that is closing bracket dot, where also we find the dot is on the extreme right, so no additional items can be added. So, we have started with the state number I0, and we have computed the states up to that is I11. So, we have around that is 12 number of states being generated as a result of the canonical items computation for the given argument, that is given grammar, that is the expression grammar with no ambiguity. So, this is how we are computing the canonical items. So, what we have to do next is going to be the parsing table construction. So, as far as this episode is concerned, we have seen only the items, that is how we are computing the LR of 0 items, which is actually needed for the computation of your SLR parsing table. So, as far as the questions, you may be given any grammar. The one grammar is the assignment statement grammar, or even S derives CC or and C derives small c capital C or D. So, you may be given any grammar, and we will be asked to compute the LR of 0 items, provided you are interested in generating the SLR parsing table. But if you go for the generation of CLR parsing table, then we will go for computing the LR of 1 items. So, with this I complete this episode. Thank you all.